are vast, ranging from food chemistry to pharmaceutical applications, and an emphasis of NMR and Fourier transform infrared spectroscopy techniques as his main research tool. So thank you, Colnago, for accepting your invitation, and the screen is yours.
Oh, I'd like to thank you, Sonia, and the whole organizing committee for giving me the opportunity to talk in this workshop, Benchtop NMR from academia to industry. And also, I think there will be some overlaps with Thiago's presentation, but I think I will give you some extra information, okay? As Sonia said, my name is Luiz Alberto Colnago. I'm trained from the Embrapa, is a Brazilian corporation for agricultural research, but I'm also professor at the Institute of Chemistry of São Carlos, from the University of São Paulo, where we do application in agriculture and in non-agriculture problems, okay? As everybody, at least in chemistry, know, any basic spectroscopy instruments, you need electromagnetic source, like in infrared or UV. You need a source, electromagnetic source, a sample holder. It contains the sensor and detector. NMR and some other techniques, we need something else that is one magnetic field. I think Thiago already explained. NMR, we need always to have our sample immersed in the magnetic field. Sometimes the magnetic field could be even the Earth's magnetic field. Because the NMR is based on this Zeeman effect. When you have no magnetic field, all the transitions that we want to observe are in the same energy levels. Okay, there is no way to see the transition, but in the presence of magnetic field, we start to see several levels. In 2 levels, in this case, you have this type of energy here. One that is the interaction between the magnetic field in magnetic moment and minus magnetic moment in B0. But what we do is not measure the energy, but measure the difference in energy between these 2 levels, and is proportional to the zero magnetic ratio, gamma. That's a constant for each nuclei magnetic field in the Planck constant divided by 2 pi, okay? And this is a basic NMR instrument. You see, we changed the names here, because NMR is a radio frequency spectroscopy in the electromagnetic source. As in radio, we call as transmitter, and the sample holder, we call, Thiago already told you, a probe where you put a coil, and what the transmitter does, it sends the radio frequency here, and this coil transforms this radio frequency in one oscillating magnetic field called B1. And the direction of B0 has to be always transverse to the B1. And like in the radio frequency, our detector, we call receptor. Then NMR has this special characteristic because it needs a magnet in all the electronics. Normally, it's closely related to radio transmission or radio broadcasting, because we have a transmitter like in a radio station and a receiver like the radio that you have in the car and the cell phone now, and we used to be having the house, okay? That's the way that we treat it. And the magnetic field is not important only to open the frequency open the energy levels in different levels, the level, but also is important because the sensitivity depends on the power 32 of the magnetic field. When we increase, for example, the magnetic field in order of 2, we have a gain sensitivity in the order of 3. Okay, if you go from 400 to 800, we get sensitivity enhanced by 3 instead of 2. And also the magnetic field is very important for the resolution, because the chemical shift, as Thiago said, is related to the chemical environment of the nuclei, it increases linearly with B0, the magnetic field. And that's because these two properties here, the NMR people want to go to the highest field because they have the highest sensitivity and highest separation in chemical shift. Okay, if you calculate the chemical shift in ppm or delta, this doesn't increase because it's normalized by the resonance frequency. But chemical shift increases linearly with the magnetic field. Also, the magnetic field is also responsible for the line width, because depending on how the magnetic field change inside of the sample volume, they give you different resonance frequency. Then we have to be careful to have a high resolution experiment, minimizing this magnetic field inhomogeneity. Normally, the line width of half height is proportional to 1 by T2, where T2 is called the effective T2. That is the time decay that we observe when you have a FID. When in FID is T2 star, it depends on the sample T2, that's a property of the sample, but also depend on the magnetic field homogeneity or inhomogeneity. And for these two benchtop equipment that we will talk later, this complement here could be minimal for middle resolution or intermediate resolution NMR, but for low resolution, this term here is so big that it almost 100% of this decay here depends of the magnetic field. This sample doesn't have almost no effect. Okay, I just show you the type of benchtop, low field or low resolution. Normally, the magnetic field is normally below 1 Tesla, and the magnetic field inhomogeneity is much larger than 10 ppm. That's normally the range of chemical shift for hydrogen. And most of the magnetic field is almost not standard, but is about 0.5 Tesla, but is 20 megahertz. But there is some commercial instrument that works with 2 megahertz, 10 megahertz, 23 megahertz, and so on. And this, as I told you, in these magnets, the line width is much broader than the chemical shift dispersion. Then there is no chemical shift, so it's not necessary to perform the Fourier transform like in high-resolution NMR instrument, okay? And that's why sometimes we call it time domain NMR, because we do the analysis on the signal in the time domain, not in the frequency domain like normally do. What we do, Thiago already said, we measure, for example, the amplitude of FID, amplitude of echo, relaxation time, diffusion, and several other parameters we can measure with that. A good thing about this measurement for FID is just to measure the amplitude. When you do the Fourier transform, you have to calculate the area of the signal. So it's much easier to acquire and process the signal in this instrument than in high resolution, because you just measure the 1 point is equivalent to the concentration, okay? In low field, mid resolution, normally the magnetic field is in the order of 1 Tesla or higher than 1 Tesla, and the magnetic field homogeneity is lower than 0.1 ppm, and there is some commercial instrument, at least that I know, from 1 to 2.3 Tesla, 42 megahertz to 100 megahertz. And the application is similar to the high-resolution NMR. You can see chemical shift, spin coupling. You can measure area for different chemical groups, and so on. And this is a comparison between the two signals, Fourier transform signal from these two equipment. The blue line is low resolution or time domain NMR. And you see the line has in the half height here has about 100 ppm. That's 10 times larger than all the chemical shift observed in the protein spectrum in high resolution. And And this shape here doesn't depend the T2 of the sample. It's always controlled by magnetic field inhomogeneity. If I put water, other solution, ethanol, any other material in solution or in liquid state, it will give you exactly this shape, okay? Because the decay of the signal is dependent of the magnetic field inhomogeneity. This is the kind of the signal that we obtain, for example, in middle resolution, but then we can see chemical shift, all these other parameters. But if you put the two together, this one is almost not able to see anything because this signal here is so broad, okay? And I will talk to you some classical design to make magnets. And the classical one is the called H-type magnet. We have two magnet pieces here, permanent magnets, and called steel yoke. There's like a box where these two magnets are placed, and the magnetic lines or field are, the circuit goes through these lines, and you can have a solenoid coil. Here are one example of this magnet from one of the manufacturers. They use as a permanent magnet. Our nickel 5 is an old magnet, but very stable and very hard material. But you can use more magnetic material that gives much higher magnetic field. And like this neodymium iron magnet, and this magnet is only this part here. Then you can make very smaller magnets, okay? Also has this C-type magnet that's just this, almost identical to this one, but sometimes we just remove one of these sides here and to have open access. If you want to do some experiment, for example, measuring something in a plant, in a greenhouse, this is the type of design that people normally use, because you can put a plant from this direction here, just wrap the coil around the branches or the fruits whenever they want to analyze. But the new designs are based on Halbach configuration and Halbach magnet. There is no yoke, there is no iron or steel in this design of this magnet, and the magnet is only made using magnetic parts. They have to have this kind of orientation of the magnetic field. You can have this two one here. We can have with only four pieces. We can have these two here and these two here, or you can have 8, or this one is made with 16 magnetic pieces. They have to be oriented in this direction. You can have 33 or 64. You can have always a power of 2 numbers of magnetic parts. And the magnetic fields come here and return all around here and make a quite homogeneous, strong magnetic field. One of the first publication, not the first, but one of the first publication using this type of magnet for middle resolution NMR was published by a group of Professor Blanche. You can see here one of these Halbach magnet. I think this was 1 Tesla, 42 megahertz. This is the size of the NMR tubes comparing, or here is the front view, is a dime here. You can see the size of this magnet. Because they don't have any iron yoke for the close the magnetic circuit. It can be very light and can produce it very high magnetic field. We use this for middle resolution or also for low resolution, as I will show you later. A few years ago, we developed another type of magnet that has, say, not exactly like the Halbach, but Halbach sometimes is not easy to assemble, to have a very good, for example, homogeneity inside here. There is a lot of tricks, not an easy thing. And we developed one that we have now a single magnet piece with a hole in the middle, and the magnet in here, you see all the magnet lines here point in different directions. But in this one, all the lines point in the same direction, but you need to have this steel yoke to close the magnetic field. And the magnetic field make a turns here. And we also can use this type of magnet. At least theoretically, it should be have a very high homogeneity magnet, but we're still having problem with the manufacturer of the magnet. They're still not making this magnet with good performance, okay? But is also is much smaller than the H-type or C-type. Then you can use, at least for this month, for low resolution NMR. And also they have this unilateral or remote or unilateral NMR. We can have this magnet, just two magnets bar on top of iron or steel bar. You can have the magnetic field in this direction, and we can put the coil here. And also we have B0 in this direction, in B1 in this direction. And for example, this is one of these magnets that we have been using. You can see, you can put a sample like an apple on top of it. But in this type of magnet, the size of the sample is not limited by the size of the magnet probe. With this magnet here, I can place against the wall and measure, for example, the moisture in the wall, and I can place in a tree. There is no limitation about the sample size. Even a cow, I can put it in the back of a cow, for example, measure the fat content in this animal. And there is also some type of magnet that are very small, for example, the size of a dime or $1 coin, okay? And these are some of the instruments that have in the market. And these four are manufacturers that will give talks in this workshop. This is one Brucker made in Germany. This is a FIT made in Brazil. This is Spinlock made in Argentina. This is a Stellar made in Italy, okay? But there is other manufacturer. Some example of NMR spectrometer with middle resolution, that's Magtech. That probably will see some presentation from them, Brucker and Nanalysis, okay? And these are three of the, but there is also other equipments in the market. What's the major difference between these two types of NMR instrument? Time domain NMR or low resolution NMR is it's a much simple instrument. For example, we don't have to do shimming of the magnet, for example, because normally it's doing in the factory or just when you arrive to the lab the first time. You don't have to do it daily basis, like you have to do in the middle resolution or in high resolution, because as I show you, the magnetic field could be very inhomogeneous. Another thing that you have to do in this high resolution is lock. Lock is a way to maintain the magnetic field very precise. Okay, then you have in a lock system, you contain NMRs detector can detect the resonance frequency, and also you can actuate increasing or decreasing the magnetic field using a coil to compensate the variation due to temperature or other problems can get around the magnet. But in time domain, there is no need for lock. Tuning and matching, that's a procedure also that's need for high resolution MR, middle or high resolution, but there is no need for daily tuning, for example. Sometimes this tuning that has been done by factories stay years. Sometimes you have to check, because in this kind of instrument, we use a very low quality resonance circuit, and if you put change with different composition or different material, it doesn't shift the tuning and matching too far. That's not enabled to perform the measurement. And also, we analyze the signal in the time domain. It's not necessary to Fourier transform the signal, okay? And the magnet temperature is quite important in low field, because the magnetic field is very dependent of the temperature, but in middle resolution, as the line with are very sharp, It's very important, even when you have or you have to have a very good lock system to keep the variation in the temperature, not causing line broadening in the spectrum. But both of them has to have a very good temperature control system, but this one even much better, and also this lock system. Okay, and normally the temperature of this magnet is almost always about 20 degrees above the room temperature. Easy to control it. Okay, and this low field NMR, normally the application, as Thiago said, is in the quality control, industrial quality control. There are several certified methods by all these international agencies. The application, certified application for food, for agriculture, petroleum, cosmetic, in polymer industry. But also there is some research to do some process control, reaction monitoring. As I think Sonia asked, there is still a lot of need to develop new pulse sequence and new processing tools. And like inverse Laplace transform is not as simple as Fourier transform. It's a ill-posed problem, and the user can set some parameters. You can see different results. Then you needed to have more stable processing tools for low field NMR. Just to show you some example using some of the magnets, probably is not available everywhere, but we have here one magnet from Spinlock in Argentina. We have a board here with 10 centimeter, 1 liter coil. Then you can put a whole bottle of wine, and this is a kind of CPMG signals or T2 signals that we observe for Brazilian, is this red, and Argentinian wine. You see here, the Brazilian wine has a much faster relaxation time than Argentinian wines. If you go to the United States, you take wines from Napa Valley or from Washington State, you can see clearly the two patterns due to relaxation time that I will explain later why. If you compare wines from, for example, Portugal and Spain, also wines from Portugal has a much shorter T2 than Spain ones. And that is why, because we found there is a almost linear correlation between the transversal relaxation rate and the manganese content. If we plotted the transversal relaxation against the manganese content, you can see almost a straight line, and the wines from Brazil, these green ones here, is all of them are almost here. Some Portugal wine are here, one USA, in this with minimal manganese content. There are some Argentinian wine from Uruguay, from Spain, and from United States. Normally, wine also has other two paramagnetic ions that interfere in the relaxation, and one is copper-2, but this copper-2 is in very low concentration comparing to iron or manganese, and also is not efficient. Is not efficient as manganese to reduce the relaxation time. Iron has a similar concentration of manganese and wine, but there is no correlation. And because we think the iron 3 or iron 2 ions are bounded to some organic molecules, and the ethanol and water cannot have easy access to these molecules, and then it doesn't interfere in the relaxation time. Another application, again, with intact bottle can, for example, observe in Brazil, it's quite common, you adulterate olive oil with soybean. If you plot the T2 value against the soybean and the olive oil, and a lot of blends here, the mixture between these two oils, you can see there is almost a linear curve between the blend of, that's not, it's a fraud, yeah, because it's not on the label. You can see you can have 10, 20, or 50%, and sometimes in Brazil, most of the adulteration, it happens in this area here because the people want to make a lot of money, okay? But also we can use it, for example, principal component analysis. We can easily you obviously see we have here also olive oil from all over the world, from Europe, Portugal, Spain, Italy, Greece, and Argentina, and Chile, and other. But these are type of polyunsaturated fat acid oil that we have in Brazil, like soybean, corn, sunflower, and this is the adulterated oil. But there is a problem if you want to use this method in Europe, because one of the ways that people use to adulterate olive oil is adding hazelnut oil. And it will be exactly here, because they have a very similar fat acid composition to the olive oil, okay? Then this method probably won't apply in Europe, or when you are using oil with high oleic content. And some applications for middle resolution, as before, there are still, these has been introduced in maybe 10 or less than 10 years. There is still a lot of research for new pulse sequencing and methods to enhance resolution, enhance sensitivity, like hyperpolarization. You have to add gradients to improve it, and also processing tool. As in this instrument, the resolution it's much lower than in high field NMR, okay? But there are already some application in reaction monitoring, quality control, profiling some sample, and processing monitoring. I think all this application here will be shown by some of the manufacturers during the presentation. Just one example, it's very easy to do, for example, monitor a chemical reaction, because this is very small magnet or instrument. It can be even a hood. You can do the reaction here and pump the reaction media to the NMR coil. But we also can do, for example, electrochemical reaction or in situ. This Kolbe reaction is one reaction. Normally we remove a CO2 molecule for two organic acid. We remove two CO2, we produce an octane molecule when you use valeric acid. And we using 1 Tesla, you can monitor as a function of time the disappearance of valeric acid and the formation of the N-octane. This all doing this 1 Tesla middle resolution instrument, okay? You can do a lot of stuff using this instrument. But the miniaturization is not limited to this. These are types that are commercially, but there is some equipment now. They are the palm size NMR. I think there is some that's already being commercialized, but they are planning in the future, the NMR will be in the smaller than a finger, and we don't know the future. And this is one example of one of this whole instrument. These are the magnet. The coil is inside of a hole here. It is all the receiver and transmitter. If you see the size of the integrated circuit, is just 1.4 millimeters. Okay, in this one paper 10. After that, there are probably 10 to 20 new types of these magnets. And I let my presentation with the organizer, and they can give you a copy. But you can see here all these reviews, or can give you information about this magnet for benchtop, and for even for these very small system like NMR on a chip. Small is beautiful, progress in miniaturization, palm NMR in one chip NMR. Then all this will be much discussed in this presentation. And again, thank you very much for inviting me and for the audience. And this is my email. And that's where we have our NMR labs, one of our building, the high field or high resolution in this floor, and the low resolution or time domain NMR are in this floor here. And we are welcome if someone wants to visit our lab, because we not only apply, but also develop some specific applications and pulse sequence dedicated to some specific analysis.
Thank you, Colnago, for the very good talk and wide variations of instruments that we have at the moment to choose for our applications, talking about Benchtop NMR. Well, any questions from the audience? No. Do you have any? Let me see the chat. Don't think we have. Please don't be shy. Ask your questions. And I have one myself, Colnago. Is there a limit of the size of magnets and the magnetic field that you can go, right? Have we achieved the smaller size of magnets with the highest B0, or we can go further?
Well, this is a trick question. We don't know about the new materials to make magnets. And at this moment, I think probably this palm size instruments are available. That very small one that was in the finger, probably still a dream, yeah? But there is at least no limitation for this, depending on the new materials, new magnetic material that probably be in the future. And for some application like low resolution, you don't need homogeneous magnet. Then, for example, relaxation, there is some instrument already for measuring some in blood that are already very small, because they put a sample. The only limitation is the sample, at least the part of the sample that will be analyzed will be very small, because all these magnetic field that you can use in almost any size of the sample, they have a very strong magnetic field gradient. You can choose a very thin slice of the sample that are being analyzed.
Okay, thank you very much for the nice talk. And I think we've moved because we